All right, so this is part 2 of lesson 6.2 where we're looking at volumes of revolution. This time we're rotating more complex areas around the x or y axis or even other axes, as we'll see, and creating 3D shapes, and we're going to calculate their volumes. If you haven't seen the disk method in part 1, you might want to go back and watch that first video. Okay, so we're going to start with this example here. So this time we are rotating this area that's between root x plus 3 and root x plus cos x. Okay, so we get this orange area. We're going to rotate that around the x-axis, and I'm going to show you in a second using my Desmos animation what that really looks like. And we get this curve that this shape, this 3D shape that we see here that kind of looks like a bowl with like a hole in the middle, right? Because we have this space between this g of x curve and the x-axis. So this time, what's going to happen is we're going to have these donut kind of shapes, these flat sort of discs that we're going to call washers that have a hole in the middle, and we're going to add up their area to get, or their volumes to get the volume of the entire shape. So let's have a look at my animation here. So this is how we start out. We have this, right, just like we have in the notes there, we have this shape that we're going to rotate around the x-axis, and let me show you what that looks like as it goes. I just have to find my rotation here. Okay, and we get this, so we're going to be calculating the 3D or the volume of this space that gets created in the middle there. Okay, let me show you a visual of the discs that get created. Okay, but we see those circles being created again. Let's visualize the washers. I'm going to take these off for a second so we can see them. Okay, so we see that they have a hole in them, right? We see all of those washers there, and we could sort of imagine these washers being added up from x equals 0 all the way, right, to x equals 4. So we're going to add up the volume of all of those washers, and we're going to imagine them being infinitely thin so that we can set up our integral and get the exact volume of this shape. Okay. All right, so it's going to be a pretty similar calculation to before when we did the disk method, but we're going to have to deal with that hole in the middle of each circle. Okay. All right, so let's do some labeling here for this. So this is the same example you were just seeing in the animation, right? We see these discs being created, but they have a hole in the middle. So essentially when we want to find the area of each washer, okay, it's going to be the area of the large circle or the outer circle minus the area, oops, something wonky just happened with my pen there, area of the inner circle. Okay, the outer circle is going to have, okay, it's hard to label it on here, but I can label it like this maybe, okay. The radius would be that length there. Actually, I'm going to just move my label here. The area, or sorry, the radius of this one, okay, I'm going to call this R out, okay. It's going to be the y value of that outer curve, right? And then the inner radius, which is harder to label, will be this distance here. And it'll be the y value or the y coordinate of that inner curve, okay. So it's going to be pi times y out squared minus pi times y in. Sorry about that dinging. I'm just going to turn that on silent. Okay, y in squared. Okay, for the outer curve, the y values happen to be equal to root x plus 3. And for the inner curve, that's closer to the axis of rotation, that's going to create that hole in the middle, the y values happen to be root x plus cos x for this scenario. Okay, so we get a much more complicated integral to evaluate, but that's just the nature of these problems. Okay, so then the volume is going to be adding up all of those washers from x equals 0 in this example to x equals 4. root x plus 3 squared. That's the area of the outer circle that gets created. If you want, you could draw it on here, right? So the outer circle would look something like this. Its radius would be this distance here, right? And it would be the y value of that upper curve. And then the inner circle that gets created is something like this. And that distance would also be the y value, but it's the y value of the curve that's closer to the axis of rotation. Okay, so pi times root x plus cos x. We're not going to solve this one because it's a pretty complicated integral to evaluate, but setting it up kind of gives you an idea of how we would do that. Okay, so we're going to practice doing this a few times. Let's do the first example here. So I've drawn this one out for you. So we're rotating this time this area between y equals x. We know this one is y equals x because it's the linear one. And y equals x squared. So this one's y equals x. This one's y equals x squared. Around the x-axis. So we kind of get this sort of cone that has different thicknesses as we go along it, right? And so the outer radius is going to be the y coordinate of the outer curve, which is x. Okay, and then the inner radius, maybe I'll use a different color, it's kind of hard to see, right, is the y coordinate of the inner curve, which for this function happens to be x squared. Okay, so when I set up my integral, I'm going to get something that looks like this. The area of one disk, or one washer, I should say, disk with a hole in it, is going to be pi times, so it's going to be the outer one first, x squared, minus pi times x squared, right? Remember, this is the outer radius, and this is the inner radius. And then the bounds for my integral, right, we can look at the picture and we see we're adding up these washers from x equals 0 to x equals 1. So I'm adding them up along the x-axis, so we're going to be integrating in terms of x here. All right, and let's set up our integral now. So the volume of this 3D shape is going to be from x equals 0 to 1. And you can actually factor out the pi and leave it on the outside if you want to. So it's going to be x squared minus x to the power of 4 dx. I got the 4 just by simplifying that expression there. And we will do the antiderivative. This one is not too complicated. It's going to be 1/3 pi, not pi, x, what am I doing here? There we go. X cubed minus 1/5 x to the power of 5, evaluated at 0 and 1. And so you end up getting 2 pi over 15 as your volume. Remember, you want to leave that as an exact value. Okay, good. Let's do another example. This time we're going to rotate around a vertical line. So this one is interesting. So we're going to be doing the same two curves, but this time we're rotating around a vertical line. So we want to change everything around and write everything in terms of y, because we're going to be adding these disks up in the vertical direction, so we're going to be integrating in y. So this curve here, the linear one, remember, was y equals x, and this curve here was y equals x squared. So if we flip that around, it's going to be x equals root y. Okay, and we're rotating around not the y-axis, but this line y equals -1. So it's going to extend the radius longer than if we were to rotate around the y-axis. Okay, so I'm going to do my best here to draw a circle. Okay, so that's the inner radius. That's not the best circle. I'm going to try again. Oops. Okay, so let's try again here. If you look on my answer key of the notes, I do a much better job of this, but I didn't do that super symmetrically, but that's fine. Okay, so the inner radius is going to be extended by this extra distance of 1. So it's the x coordinate plus 1. So for both radiuses, our in is going to be the x coordinate plus 1. And the inner function here is the y equals x function. So it's going to be y plus 1. And then the outer radius is also going to be the x coordinate plus 1, right? But it's going to be, so I'll just do r in here just to make it clear. All right, and then so for that outer function, it's going to be root y plus 1, okay? It's plus 1, again, because the radius is extended by 1 unit farther than it would be if we rotated around the y-axis. Okay, so let's set up our volume then. So we're going from y equals 0 to y equals 1, and we're going to have pi times, so it's going to be the outer radius squared minus the inner radius squared, okay, dy. And we're integrating in y because these discs are being stacked vertically. If you have a look at my answer key, the notes, I do a much better job with the visual, so you can look there. It's just hard to draw it by hand. Okay, and we'd have to multiply this out and then do the antiderivative to get the final answer. I'm just going to do one of the steps and then show you the answer if you want to kind of pause and see if you can get the same answer. I'm not really testing you on your ability to solve integrals in this unit, so I don't want to spend a ton of time in my lesson going over that. So if you expand this out, you get something like this. You'd collect like terms, do the antiderivative. So I'm going to put dot, 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 okay? And then the answer comes out to pi over 2, which is kind of cool that it's such a nice number at the end. So the volume we get here is pi over 2. Okay, let's do one more example. Same region again, this time rotated around a different vertical line. This one's kind of hard to see, so or the radius. I feel like students usually struggle the most with ones like this, where you're rotating around a line that's in the positive part of the x-axis. So, okay, so let's try and draw. This will be easier to draw one of the washers because they're not as big. Okay, so we're rotating around here and we get this. Okay, so our washer looks something like this, and what I'm shading in is the area we want to look at here. Okay, so I'm going to label two things. I'm just going to focus on the outer radius here. So the outer radius is this distance right here. Okay, now I'm going to label a couple of things on this graph to get us to see what that value is. So I'm going to label this as r out, right? It's the distance between the middle of the circle and the outside of that outer circle. Okay, now if I were to label this distance, which is far too big, right, to be the radius, but that distance is always equal to 1, just because the distance from the y-axis to whatever we're rotating around here is 1 in this example. Okay, and this distance from this point to the y-axis is going to be our x-coordinate. Okay, so we see how if I highlight those two pieces, the outer radius is going to be the 1 highlighted in yellow, right? That's too big, minus x. It's going to be like the difference between those. Okay, and in this example, the outer curve there, remember, is y equals x. So it's going to be 1 minus y. So I'm going to put in brackets since y equals x for the outer curve. Okay, and then similarly, the inner radius will be the same. It'll also be 1 minus x. Okay, but for the inner curve or function, as you remember, x equals root y for the inner curve. Okay, so our volume is going to be, and we are stacking these vertically, so we're going to be integrating in y, so we're going to integrate from y equals 0 to y equals 1, right? So we see that region here. And we're going to do pi, and it's going to be the outer radius squared minus the inner radius squared dy. Okay. Again, I will spare you the details of all of that, but basically you expand it. I'll say equals dot, dot, dot. Okay. You could try this on your own. So you expand it, collect like terms, do the antiderivative, and you should get pi over 6 as your final answer. Okay. Yeah, so that takes us to the end of the washer and disc lessons.